Good afternoon, system engineers of the world. Welcome. Our next keynote will be presented by Dr. Ronnie McKenzie and is entitled Water Supply Systems, a Broad Overview. There's an old saying, when the well is dry, we will finally understand the value of water. We are rapidly approaching that situation throughout the world. That's why this keynote is important. Ronnie was awarded a PhD in civil engineering from the University of Strathclyde in Glasgow, Scotland. For the past 20 years, Ronnie McKenzie has been the managing director of WRP, a South African company that specializes in water demand, water resource management. He was a key member of the Vaal River Systems Analysis team that pioneered the water resources systems analysis techniques now used throughout South Africa and many other parts of the world. He was also involved in the Orange River System Analysis, the Namibian Central Area Water Master Plan, and the verification of the Lesotho Highlands hydrology for royalty calculation purposes. Ronnie is well known for his key role in the Khayelitsha pressure management installation and the Sebokeng advanced pressure control system. Both won awards for technical excellence. He also has an extensive international footprint as the past chair of the International Water Association's Special Group on Water Loss. He has presented more than 50 workshops on pressure management, water demand management throughout the world, from Ethiopia and Brazil to New Zealand. He consults to the World Bank, the European Union, United Nations. But Ronnie McKenzie is a man of many talents. He has published a book entitled Meteorites, a Southern African Perspective. It's available on Amazon, also in a Kindle version. His interest in collecting meteorites spans some 30 years. So the keynote will be presented by Dr. Ronnie McKenzie on water supply systems, a broad overview. Thank you, Ronnie.
Thank you. Okay, good morning or good afternoon, everybody. It's a privilege to be invited to give you another presentation, and I just wanted to say how honoured I am at being invited back to INCOSE, and to just tell you how much I enjoyed the Seattle conference back in 2015, and I hope that I can keep you awake for the next hour. I just also want to thank Ad Sparius and Renee Oosthuizen from the South African chapter for inviting me back, and we'll try and kick off, I think, see if we can get this working. Let's get this going. Yeah. Before I start, I was looking at your website, and I noticed on your INCOSE website that you've got a certification process that's at 456 views, and I noticed that there's another one where you can be certified in 3 easy steps. It's got 3,500 views. So I decided that I would change my title to Understanding Water Supply Systems in 2 Easy Steps, really. So I hope you don't mind. We'll change the title a little bit here. Before we get started, I just wanted to touch on a few things about what you're missing in Cape Town. You were all supposed to be here, and unfortunately COVID has stopped that one. I remember from the Seattle event that you like competitions, so I was going to kick off with a little bit of a competition where we'd ask you a question and you'd get a prize, and I was looking at a few prizes. We're going to have 3 prizes actually. One was a car, a big Bentley Continental. And the second prize was a bottle of South African wine. And the third prize was a 2-week cruise. Now, this is a sort of Scottish raffle, we call this. You'll figure out what that means at some point. Anyway, the prize would have been the wine, I have to say. And in South Africa at the moment, we're now on a lockdown for wine and alcohol. So we have, so the bottle of wine would have been quite popular. I think people would have chosen it over a 2-week cruise somewhere at the moment. Coming back to South Africa, you know what you're missing. Some of you have been here before. It's got lovely coastlines. Cape Town in particular is a very nice part of the world. It's one of my favorite spots. Some lovely scenery. This is Camps Bay, which is next door to the conference centre. You've got big shopping centres. You would have been able to go there. Also, there's a new museum right next door to the conference centre called the Silos Museum. As you can see from the picture there, it's an old silo that was built hundreds of years ago, and it's been converted into a very large and impressive museum as well as a hotel complex. Inside, they've cut the silos out, and they've put in lots of exhibits, etc., that you would be able to visit. This museum is apparently it's one of the top 10 in the world. It's been rated for its architecture, etc. It's got lots of exhibits. Unfortunately, I think they ran out of money towards the end of it, and this is one of the exhibits that you can see there. It's basically, I think it's called the Pile of Bricks exhibit. It's just basically some bricks and a bit of string. So I think when the money ran out, they managed to do this one. It's good quality bricks, I have to say, but I think this is the sort of exhibit that you'll probably see more and more in museums around the world now. But anyway, it's well worth a visit if you do go there. Other things I just wanted to touch base. If you do come to South Africa next year, you'll obviously go to the game park. In Seattle, I did talk about the big 5 and the little 5 for austerity measures, etc. I thought I'll just give you a couple of tips this time. Just be careful if you're in the game parks. The lions are quite smart. They operate in packs. The females are running around creating emergencies all over the place, and the males will be lurking behind, just waiting to see who turns up. Outdoor showers are quite common in most of the game parks, so you just have to be careful. If you have a shower, just watch before you go into the shower who's there. Elephants, always close your windows. Don't tease the elephants. They don't like being teased too much, so you've got to be a bit careful with the elephants. Some of the game parks, you can hire bicycles. They even have races through the game park. For mountain bikers, most people do their personal bests in these conditions, so you should do quite well. Just make sure you can cycle at more than 25 miles per hour, which is the top speed of the elephant. You won't be able to outrun any of the other big 5, like the lions and the buffalo and such like. They go at between 50 and 40 miles per hour. So just make sure you can go faster than your partner, then you should be safe, I would think. Yeah, that speaks for itself, that one. From personal experience, this is, I actually can tell you from personal experience, this is next to my house here in Pretoria, of all places. A zebra can run at 40 miles per hour, and one of them took me off my bicycle when I was out cycling. I'm not sure if it's the one at the back there that's lurking in the undergrowth. It did give me a dirty look as I went past, but I can tell you from first-hand experience, zebras, you don't want to hit them on a mountain bike. I remember from Seattle, I think Jan Bosch from Nokia was telling you what car to buy. It was a Volvo XC90. As far as mountain bikes go, I would recommend a Cannondale. It can withstand a zebra attack. Okay, background, water supply systems in South Africa. Let's get back onto the topic of today. Africa, as you know, is it's the continent of Africa. It's pretty large. It's got lots happening in it. South Africa is a little bit at the bottom. That's where I'm based at the moment. That's where I'm talking to you from. The South African water supply system, I mentioned it previously. I'll recap a couple of slides. So those that were in Seattle may recognize one or two, but the talk is quite different. South Africa's got one of the most integrated and complicated water resource systems of its type in the world. We are transferring water from one part of the country to the other, often over distances of 1,000 kilometers or more, and through mountains, over mountains, round mountains, you name it. This is going to happen more and more all over the world as water becomes scarce. It's already scarce. I showed this picture previously. This is the Orange River Basin, which is 1 million square kilometers of the Orange River. This is probably the most integrated water resource system of its type in the world. We're currently looking at a new transfer from Lesotho as far up as Botswana. Botswana is looking at the potential for transferring water from the Lesotho Highlands, a mountainous region with excess water, up to Botswana, which is pretty arid, quite flat, and has got water issues. It may or may not happen. It's currently being looked at and investigated. The other one that people keep considering, especially after the recent Cape Town problems, is moving water from the Orange River down to Cape Town. That's about an 600, 800 kilometer transfer that would be pooled into this huge integrated water resource system. I mentioned water resource systems in the past. Just to touch, I'm not going to go into in any level of detail. Basically, we take a map of an area, which is fairly simple. We identify the resources, the dams, the channels, etc., etc. We identify the demand centers. We then develop a systems model, which is basically kind of complicated. We make it really complicated, and we add linear programming and dynamic programming and out-of-kilter algorithms and anything that makes it really, really complicated. And then we analyze it and we run it through 1,000 plausible sequences of weather patterns, and we get lots of potential results. We use these models in order to operate very complicated and integrated water resource systems. And we supply the different demand centers at different levels of reliability. That is a key element of a major water resource planning analysis. Not every demand center gets supplied at the same level of assurance. Farmers, for instance, would be supplied a 1 in 20 year risk of failure. A city would be supplied perhaps a 1 in 100 year risk of failure. A power station at perhaps a 1 in 200 year risk of failure. We don't go above 1 in 200 years. It becomes a bit academic after that. This slide is a sort of 5 meter across map of the system, the Orange River system, which I mentioned is one of the most complicated of its type in the world. You can zoom in on it. and you'll eventually get down to one of the big dams or one of the small dams in the system. That system is made up of 87 major dams, almost 300 smaller dams, 1,250 demand centers or abstraction points, 4,000 connections like bits of a river, canals, pumps, that type of thing, and 300 naturalized inflows. Again, I'm not going to go into the detail of this. It's all documented somewhere on the internet, so you can find out more if you're so inclined. What's important, and we mentioned this, we've mentioned this a couple of times, is that the larger the system, as you develop very large systems, like a 1,000,000 square kilometer system, it increases the critical periods and you end up with a 15-year critical period instead of a 3 or 4-year critical period. Natural droughts in South Africa tend to occur every 10 to 15 years, naturally. So this slide here is a bar chart showing you the storage in the reservoirs for the whole country of South Africa. The top of the bar represents the total volume, and the blue part of the bar represents how full the dams were at that specific time. So where you see a lot of the yellow, that represents storage that is not full, it's not got water in it. So where you see a lot of yellow, that represents a drought event within this 100-year record. And you can see over the 100 years, there's about 6 or 7 drought events, and these are natural occurring events. It's often very easy to blame climate change on everything. It's very easy to do that, but you need to bear in mind that droughts do occur naturally, and that climate change may increase the frequency of the droughts, or it may make them worse than they would otherwise have been. But with or without climate change, you will still get droughts and you will still get floods. Now, Cape Town, what happened in Cape Town? You've probably seen it on the news since 2015. There was quite a lot happening in Cape Town. It was a daily thing on the news. Cape Town, being at the bottom of the African continent, tends to receive winter rainfall due to cold weather fronts coming through, and it's a climate system model that they've got. So the cold weather brings rain to the Cape. What happened over a period of 3 or 4 years was that we had some high pressure systems that would come in and sit in the ocean just to the west of Africa. And these are normal events, but we seem to have more than the normal amount over that 4-year period, with the result that it pushed the cold fronts to the south and they missed the Cape. And so Cape Town ended up having a 4-year drought, which was the worst in living memory. Now, Cape Town is a city of about 4 million people now. It's an urban industrial area. 70% of the demand is urban industrial and about 30% is agricultural. It has 6 major reservoirs. I think in the previous presentation I talked about the Orange River system. We use the same techniques and modeling to analyze the Cape Town system, and there are engineers in Cape Town that are doing that. I'm not involved personally in it, but I do work with the city of Cape Town on occasion. So I've borrowed a few slides from a good friend of mine, Peter Flower, who was the Director of Water and Sanitation during the Day Zero crisis. So this slide just shows you some of the major pipelines and reservoirs. Most of these blue lines that you see are 3-meter diameter pipelines. There's a couple of thousand kilometers of large diameter pipelines pulling the water into Cape Town. This is just a schematic, a high-level schematic, showing you the water supply system. Again, it is horrendously complicated if you drill down into the lower layers, as we did in the previous Orange River system. A couple of pictures of the dams. You can see a few of the dams here in Cape Town. They've got 6 major dams that supply the city that are all linked together, and they operate the system. This is what it looked like in their Day Zero, when they were running out of water, and Cape Town was reputedly going to be the first major city in the world to completely run out of water. That was false and fake news, but it was Sky News and a few of the other big news channels ran it every day, which didn't do the tourist industry a lot of good. Unfortunately, Cape Town has been a casualty to some extent of its own success. Since 2000, Cape Town introduced some fairly aggressive demand management in order to curtail its growing demand. This slide shows that for a period of 15 years, they managed to keep the demand relatively constant, despite the fact that the population grew by about 1/3. And that dip at the end there in the red circle just shows you what happened when the drought hit and the demand had to be curtailed. So that's the demand management. Their losses were about 14.5%, which happened to be about the lowest in South Africa. Most of the cities in South Africa have water losses between 30 and 40%. So 14.5 was a very good number. A couple of pictures showing you the infrastructure in Cape Town, some of their pipelines, pump stations, etc. Water treatment works, they've got 5 or 6 big water treatment works. Now, what was quite interesting, we organised a water loss conference in Cape Town for the International Water Association back in 2018. And we managed to time it such that we were within a month of Cape Town running out of water completely in the worst drought that they've had in 500 years. Whether that was a good thing or a bad thing, I'm not really sure, but it turned out to be quite interesting. We got lots of hate email from all over the world, people sending me threatening letters about hosting a conference in a city that's got no water and how dare I do that and such like. And other people were less aggressive, but they wanted to help. People from Alaska and New Zealand wanted to ship water to Cape Town. It was very kind of them. I mean, they were being nice, they were trying to help. Interesting, you can't really get much further away from Cape Town than Alaska and New Zealand. So when my colleague Peter Flower got these invitations to have water sent to them from those countries, he was quite taken by that. Cape Town, in fact, despite all the negative publicity about how bad things were and how they didn't manage this water loss thing properly, they won quite a number of awards for their water demand management expertise and what they did in Cape Town. And they won the COP21 C40 Cities Award in Paris, which is quite a prestigious event. Not as prestigious as the IWA Award, which we gave them for being the first city in the world to reduce its demand by around 50% without going on to intermittent supply. It's very easy to cut your water demand down if you just chop it down and cut areas off. But to do it without going on to intermittent supply, that takes a lot of expertise, and they deserved all the awards that they got. This is a slide showing you the 10 years of demand, where the city of Cape Town, their demand drops. And you can see at the end, the last 3 years, it dropped down dramatically. I just want to point out, and you can go on the internet and check out if I'm telling you the truth here or not. In 2015, I made a quote in Seattle, and this was before the drought in Cape Town started. I said we were overdue the next drought and that it's on its way. Well, it came the following year, and it was a 1 in 500 year drought, believe it or not. So it was quite significant. This slide here just shows you the annual inflow to the 6 dams in Cape Town, spread back over 100 years. You can see that the last 4 years were well below the average. And to get the 3 worst years back to back, that was something no one could have anticipated. They managed it by increasing the price of water. They pushed it up to $60 a kiloliter for the top tariff if you use more than 35 kiloliters a month. They then got the penguins in to help people save water, shower for 2 minutes, report leaks, do water-wise gardening, shower with a buddy, shower in a bucket. They all did their bit, and the penguins helped save Cape Town. Cape Town managed to get through the worst drought in the last 500 years. Interestingly enough, compared to the Australian drought, which was the worst drought in Australia in memory or in hundreds of years, they had a target of 140 litres per head per day. Cape Town got down to 120. Which is quite significant. So that was Cape Town were amongst the best in the world when it came to saving water. In South Africa, now it comes to, we've talked about water resources and the systems. We now look more at the leakage side. And we introduced what they call the BABE methodology, burst and background estimate methodology, which is made up of 4 components. Now, I'm going to skip through them fairly quickly. They're all available on the internet. The software that goes with them is available freely from the Water Research Commission. It's based on the UK water industry approach of dealing with leakage in 2 forms. Background leakage, which is all the small leaks that you can't do anything about, and burst leakage, which is all the big leaks. Okay, so it's big leaks and small leaks. It's not rocket science here. We've got 4 models. This is a slide that I normally use. I get into trouble using this slide quite a lot. So I've added Stuart Hamilton there from the IWA Water Loss Group. He's the new chairman. I've passed over to Stuart. He insisted that the slide wasn't representative. So we've modified this slide. We've got 4 models: Sandflow, Bench Leak, Pressmac, and Econoleak. And these models are available on the internet. Bench Leak is basically a water auditing model where you use a water balance, and it's a standardized water balance that has been accepted around the world, including America, Australia, Europe, Africa, all over the place. So that's quite important. We talked of leakage performance indicators previously. That's part of the water auditing and the benchmarking. This, I introduced an indicator last time, the ratio of spectators to workers, which is, it's actually quite a useful indicator in South Africa, I have to say. But we've got a new one. I'd like to introduce you to a new one from a friend of mine, Prof. Mike Muller. He's actually an engineer with a sort of political hat as well. So Mike came up with this indicator, which is called the Mike Muller Mercedes Index. it shows you that that leak there is the equivalent of 1 Mercedes-Benz per month. It obviously depends on the cost of the water and the cost of the Mercedes. We're using a mid-range C-class in this case. And that leak is equivalent to 12 Mercedes-Benzes per annum. This is quite useful for the politicians. To try and get over the value of leakage to the politicians is sometimes a problem, but not if you tell them how many Mercedes-Benz cars it's worth. So this is from a good friend of mine, Prof. Muller, and this is his index. So I've borrowed a couple of slides there. There's another model. The second model was the night flow analysis model, which looks at the water going into an area at night time. And you use this to tell you whether you've got a leakage problem or not. So you monitor the water and you can see you measure the minimum night flow. You then make an estimate of what it should be, and the difference gives you an indication of how much leakage you've got. It's quite useful. This is a logging result for a 6 or 7 day period. You can see it's not too bad. The night flow is not too high. And this is another example. These are real examples of real areas that we're supplying water to. This one has about 90% leakage. And this is not unusual, particularly in developing countries. The third model is a pressure management model. Pressure management is your low-hanging fruit and something that we promote very heavily in South Africa, and it's something I've got a particular interest in. It basically involves looking at the system. The systems are designed to give you a certain pressure during the critical peak demand period at your critical point. During off-peak periods, the pressure builds up and you end up with leakage, particularly at night time. That's why most leaks develop at night, because your pressure builds up in the system. This is a pipe at low pressure with a leak, and this is it at high pressure. So you can see the difference. You can imagine at night time, the leaks run really hard at night time when no one's using the water. So we introduced pressure reducing valves. And I need to just mention that they were invented by a Scotsman, James Watt, who also helped kickstart the Industrial Revolution. So it must be good equipment, this one. They don't quite look like that anymore. They look more like this. You get some big PRVs. They're made all over the world. Good quality ones. You get American ones, Canadian ones, Israeli ones, European ones, Australian ones, Europe. Scottish, of course, will be amongst the best, I would imagine. They come in all sizes and colors, but we can also apply controllers to them that will give us extra control during the off-peak periods. This slide basically shows you a 24-hour profile at the critical point. The grey area shaded in is excess pressure at the critical point, indicating that you can cut down on the leakage if you can reduce that grey area. So we can put in a pressure reducing valve, and that will then take something off the grey area like you've got there. So you can see just using a normal pressure reducing valve gives you your biggest saving to some extent. But we can then add an electronic controller that will take the pressure down at off-peak periods at night time and maybe sometimes during the day. That then takes even more of the grey area out of the picture, so you've now saved additional pressure. Whatever you can save on the pressure reduces the leakage. And we can go to a higher flow modulating controller. That gives you probably the best that you're going to get. Or you can use closed loop control, you can use intelligent loop control. There's a whole bunch of new controllers that have come out. Everyone has advantages, and for every advantage there's a disadvantage. The maintenance is often a big issue, the reliability of the components. Sometimes you're better just using a standard pressure reducing valve with no controller. Other times you should use the most expensive, fanciest controller. There's a couple of valves there that you can see using hydraulic control. So they also are quite popular these days. Some of the big installations around the world that we've been working on, Keynote is a big installation. We saved about 9 million cubes per annum. It's a swimming pool every 2 hours. Sebo King is another big installation. That one's in Johannesburg. Similar idea there, similar savings. Both of these installations had savings of had a payback of about 6 weeks on the cost of the actual installation. So it's difficult to say how much the savings were because the exchange rates keep changing, but the numbers were big. They're certainly big. The fourth model that is available through the Water Research Commission is the EconoLeak model. I don't really like this one, it's a bit complicated, but I'll take you through a couple of things. We look at how much water you lose in a leak, and I think the key take-home point here is don't look at the size of the leak, because that's not always telling you how much water you lose. This leak lost 20 cubes for 3 hours. This leak lost 40 cubes for 6 hours, so it was 240 in total. This is a huge leak. This lost 600 cubic meters of water. Then we've got a small leak. You wouldn't think that would lose so much. It lost 2,200 because it ran for 3 months. And then another one, an even smaller one, ran for 3 years and lost 13,000. So don't ignore the small leaks. It's important that you actually sort out the leakage. High tech, looking for leaks. Elon Musk, a South African that I think you were trying to get him to come and talk at your conference. He was too busy building a rocket, I believe. But anyway, he threw up some satellites, or he's planning to throw up another 300 or 400 satellites, I believe, and they say they can find leaks from a satellite. I'm yet to be convinced on that. In the UK, they've got a dog that can sniff out leaks. There's a picture of it. It's a real dog and it can really find leaks, this one. We tried it in South Africa. We used a little greyhound and a Rhodesian ridgeback, and we used a Canadian leak detector. So you can see there the two dogs that we thought we'd give it a go. They thought they'd found a leak, but alas, it wasn't to be. So we gave up on that. We don't actually need dogs to find leaks in South Africa. We can find them ourselves. They're normally quite obvious. You don't even need a satellite to find this one. So you can often, to go the high-tech route on leak detection is not always necessary, I have to say. Using data acquisition systems, there's lots of new technology. GPRS on the GSM network. We can use Sigfox, LoRa, RF systems, pulling in information, monitoring the water going into an industrial complex or an office development or any system that you've got is actually very valuable. It shows you what's happening. This shows you an office complex over 8 weeks. You can see the baseline, there's a high leakage there, and eventually we managed to eliminate it. If we hadn't used real-time data acquisition, we wouldn't have known about that and we wouldn't have been able to find it. This is what it should look like on a normal month. You can see 5 peaks every week. There's one there with only 4. That's because there was a holiday on the Friday. So you can see exactly what's going on. You've got your water use at the weekend, nothing's happening. This is the same office complex where we've now installed a dual flush toilet in order to save water. That didn't work. We ended up with the thing stuck all the time because there was too much silt in the water for the dual flush mechanism. So sometimes high tech does work, sometimes it doesn't work. This is a growing leak that we eventually fix in an office complex over about a 6-week period. This is a similar type of thing at a private school where they had lots of leakage, and we send alarms every day until they fix it. This is an example of a leak that was running at a constant rate, and then we fixed it. I mean, this leak was 99.5% of the water demand. I mean, it's crazy, and it ran for 3 years. This is another one. This is a prison. You can see this one. They moved on to intermittent supply, which isn't a good idea. It causes air to get into the system gets messed up. You end up with all sorts of problems, and you can see you get spikes when you refill. We also look at energy, carbon dioxide and energy. We've got some solar panels next to our office. They built these solar panels for about R1 million in order to save energy and to save on carbon dioxide, save 90 tons of carbon dioxide. Compared to our pressure management installation, our pressure management installation saved 13,000 tons of carbon dioxide per annum just due to the reduced pumping, because all of the water in Johannesburg and Pretoria has been pumped an average of about 200 meters. So for every cubic meter you save, you can calculate the energy savings and thus calculate the carbon dioxide savings. So in this particular case, the solar panels were not that cost effective. In fact, they didn't have a payback. Now, we're getting to the end now. You'll be happy to hear. I was in Australia a couple of years ago, and I was chatting to a friend, Peter Rochlin, who's a sort of water resource planner, and he shared with me what they're doing or what they're looking at doing. I don't know if they've actually done it or not, but they're looking at doing some big transfers in Australia. And I thought I would share this with you because I believe it's quite interesting, and I think it's quite applicable in many parts of the world, particularly where you've got lots of sunshine and you can use solar power to generate electricity. It probably wouldn't work too well in Scotland, but certainly Australia, South Africa, Namibia, Lesotho even, probably many parts of America, this could work. They wanted to move water from a dam in the north of Australia down to get water into the Murray-Darling Basin, which supplies Sydney. I think there's also links through to Melbourne and probably water through to Adelaide. Anyway, it's quite an adventurous scheme involving 2,500 kilometers of very large canals, big canals. You're not talking about tiny canals, we're talking about big lined canals. The key and the thing that I really liked about this scheme is the fact that solar panels are quite common. I mean, we've been using them for years, but what I found interesting was they plan to use graphite batteries to store the heat generated from the solar panels. So the solar panels generate electricity. The electricity generates heat, which gets stored in these big blocks of graphite. Now, the graphite can store that heat. I think, if I'm not mistaken, it goes up to about 800 degrees centigrade, which is pretty serious as far as heat goes. It's insulated by xenon gas, I believe. I don't know the technology, but I'm sure it's on the internet somewhere. Everything's on the internet. But the key point is that the batteries can keep the heat up to about 4 weeks. And that is a game changer when it comes to storing solar power, as far as I'm concerned. And this is quite an interesting project or technology that I really found was maybe a game changer, particularly when it comes to water transfer schemes, because most of the water transfer schemes tend to be over dry areas. You're moving water over deserts and over long flat areas, and you need to pump it up every so often. And you can't get electricity there because it's in the middle of nowhere. So you can generate your own electricity here. And this is a particularly nice option, I think, if it works. I don't know how advanced it is. You'd need to check up with the Australians, but it's a very new technology as far as I'm concerned. The graphite batteries are about 23 tons a piece, and you can basically just put 100 of them in, or 1,000. You can put in as many as you want as to take up whatever solar panels you put in. It has disadvantages in that the efficiency is not that high. It's about 40% because you've got a double. You're going from electricity to heat, and then from heat to steam, and then from steam back to electricity. So you've got a double whammy on the efficiency side, but it doesn't really matter because you've got unlimited sunshine in most of these areas. So I think this is quite a nice one. The other thing about the batteries are they're environmentally stable. They don't really damage the environment at all. You can heat them up and cool them down as many times as you want. And that's, to me, this is a very interesting technology, and I hope to hear more about this in the future. And on that point, I've already been run out by the bell, so there we go. I'd like to finish there, and thanks for your attention. I hope you found it interesting, if nothing else.
Thank you, Ronnie, for a wonderful and an entertaining keynote. There are quite a number of questions. The first question comes from Australia, Tim Ferris. Does leakage create a psychological problem of people thinking that if the supplier allows leaks, they must have plenty of water? What is the point of them being very frugal in usage if there is so much water?
Yep. Can I shall I answer them one at a time? Can I answer it now?
Yes,
yep.
yes, okay. Please.
No, I think that's a great point. I think any water utility that allows leaks to just run down the road is setting a terrible example for their customers. Their customers will just ignore leaks themselves if the utility do not manage the leakage. So it's a very important point. In Cape Town, when they had their day zero crisis, you did not see a leak anywhere. Not any leak that was reported was fixed within 3 or 4 hours. I mean, they really took it seriously, and people, the sort of psyche of the people in Cape Town, they became the most water conservation specialists in the world. I mean, they really did. So it's a very good point, and I totally agree. If a municipality does not fix its leaks, they cannot expect their residents to save water. It's just won't happen. Totally agree.
Thank you, Ronnie. There's another question from Mark Winstead. He says in Colorado, population growth has strained the distribution of water. Pumping over mountains creates problems and threatens to overcome supply available in coming decades. One mechanism to help was to encourage long-term changes like encouraging xenoscaping. It was too successful in some communities as revenues from selling water support the water supply, and the prices had to keep increasing to cover overhead costs and fund long-term solutions, which in turn encouraged folks to use less. A vicious cycle for a few years. Were there any similar experiences in South Africa?
I think that's an important point as well. I think you have to balance the cost of the water, and water should be priced realistically. I mean, the water it's not in anyone's interest to bankrupt the water utility. So the setting of tariffs is a very delicate process that has to be done quite carefully. The tariff structures that I showed you for Cape Town were absolutely draconian. I mean, that to charge 1,000 or $60 per cubic meter of water. I mean, there's nowhere in the world charges that for water. So it is important that you balance it out, and you implement these changes slowly and just a small piece at a time, and you gradually nudge the price up, and you gradually then adjust it so that people pay a realistic price for water. Because most people will realize that if they don't reduce their water consumption, then there just won't be any water for them in future, and they will need to implement big schemes that will cost a fortune. So we have got examples all over South Africa where the water utilities have almost gone bankrupt due to people not using water. So it is a balance. You want them to use water when you've got surplus water to pay for the infrastructure. Another way of doing it is to have a fixed tariff to cover the cost of the infrastructure and the staff at the water utility, and then have a supplementary charge which is based on the actual amount of water used. Most places I've seen tend not to charge enough for water. And I think South Africa, if you look at the price of water in South Africa now, Johannesburg is charging industry the equivalent of $5 a cubic meter. That's quite a lot. So the value of water is becoming apparent, and people are starting to pay for it.
Ronnie, two questions. The one is Stephanie Cheesy. Have you explored using inexpensive robotic detectors that find leaks from inside of pipes? And then somebody else, Mohammed Al-Bajati, what approaches are you using to detect the underground pipe leak? I think it is hard to find a pipe leak, especially when there's a small leak.
With regards to the robot, there's a number of different technologies available to find leaks inside pipes. There's cameras, there's little smart balls that you send down the pipeline. You've got Sahara cameras and JD7 cameras, and you've got little, like you mentioned, little robotic things you send down. All of that technology has its place. The key message that I would say there is, in many municipalities that we are working with, their leakage levels are up at 30 to 50%, which is pretty high. You don't need high-tech solutions to find leaks when your leakage is up at 50%, because at those levels, you're not even fixing the leaks that everybody knows about, that are evident. There is no point going to look for new leaks until the water utility is fixing the ones that it can see on the surface. Once they've got the surface leaks and the visible leaks sorted out, then they can start on the leak location and using high-tech solutions. But at that point, their average leakage levels will be down at 10 or 15%. At that point, it does become viable to start looking for using equipment to find the leaks. With regards to the small leaks, the second question, there really isn't equipment sensitive enough to find the background leaks. And even if there was, it wouldn't be cost effective to do so. Background leakage, you can reduce in two ways. You can either rip out your network and replace it with a new network, or you can reduce the pressure and just manage the background leaks so that they don't grow and eventually become burst leaks.
Thank you, Ronnie. Question from Eileen Arnold. How many leaks are we talking about? Thousands, millions? Reducing pressure is a band-aid. What would it take to fix the leaks? Is it too expensive? Are there too many? Accessibility issues? Are there other hurdles?
I think when it comes to burst and background leakage, the the concept, the whole concept about burst and background leakage is that burst leaks are large enough and significant enough to make it worthwhile looking for them and fixing them. Background leakage is so small, you have millions of them. Every joint in the pipe may have a small, tiny trickle of water. You may have millions of background leaks. You cannot find them. They're too small to find. And if you were to find them, it wouldn't be cost effective to try and repair them because there's so many of them, and the benefit of repairing them doesn't really help you. That's why, that's the whole emphasis of this burst and background leakage. If you know that your system doesn't have any burst leakage, it's only background leakage, which does happen, then you can't go looking for them and fix them. The only thing you can do is just control them, manage the pressure in the system to manage that background leakage. Burst leakage, it's cost effective to go looking for it. You should fix it, especially reported leaks. Water utilities should be fixing reported leaks within 24 hours as a standard, and in crisis conditions, down to 6 hours.
Ronnie, here's a question from Guillermo Chalet Gongara. I'm not sure where he's from. He says, water theft, pipe hacking are common problems in some emerging countries in Latin America. Are there any specific measures to protect the infrastructure in South Africa?
Yeah, that's a horrible question. That's a hard one. Yeah, water theft. Water theft is a problem. In South Africa, it's not too big a problem because the government introduced a free basic water allowance. So every household in South Africa legally is entitled to a certain amount of water, which is given freely. And once you go above, I think it's 6 kilolitres a month, then you start paying for the water. It's part of the tariff structures. I have visited many countries where the theft of water is just astronomical. And it basically causes the water utility to be dysfunctional. You cannot run a proper water utility when your levels of theft are as high as they are. So it almost comes down to the public having to adhere to some rules and regulations. If the public want to just steal water within a short space of time, you will not have a functional water supply system, and everyone suffers. So I don't have a proper answer to that one, I'm afraid. That is not an easy problem to solve, and it is very, very serious in many countries.
Ronnie, a question from John Palmer from Boeing. He says it's a great presentation and wonderful life cycle perspective and recognition of prices as a factor in efficiencies. Question, what are some of the consideration on evaporative losses in water transport systems?
Well, when it comes to these big transfer schemes that I was mentioning, for example, in Australia, the evaporative losses in that canal system that they've been looking at, I think they're projecting about 10% of the water going in at the one end of the canal is going to evaporate and be lost. That's doable. I mean, it's not going to kill the scheme. I mean, in a normal water supply system, in a municipality, in your reticulation system, most municipalities around the world do not get down to 10% losses through leakage. Most of them are above that. So 10% in these big conveyance schemes, if it's an open canal, I would guess 10% is achievable, especially if you're using the type of lining of the canals that they've got in the photograph that I showed. If the canal is properly lined, you can get down to about 10%. If you use unlined canals, your losses in canals can be up at 40 and 50%. It can be massive. So in these big transfer schemes, you can probably get down to 10%. If you use bulk mains, like a big diameter pipeline, then you can get down to 1 or 2% on these big schemes where you're transferring big quantities of water over huge distances. You can probably get down to quite a 1 or 2% number. But the extra cost of using a pipeline over a canal is often quite significant. Pipelines are many times more expensive than canals. Obviously, a pipeline can go over hills and up mountains or through mountains, whereas a canal, it has to be properly designed, and it flows with gravity. So you need to, the area has to be flat for the canal systems to work. And you also need bridges to go over so that the animals can get from the one side to the other, and it's got all sorts of environmental issues, so you've got to be quite careful. I would say 10% losses on a big canal, 1 or 2% losses on a big pipeline is sort of the norm.
Ronnie, thank you very much indeed for a wonderful presentation. It was thought-provoking, it was entertaining, it was information-rich. Thank you very much indeed, also for answering all the questions.
It's a pleasure, and I hope your delegates enjoy the rest of the conference. Thank you for the opportunity.
It's not quite yet the end of IS2020. There will now be a 20-minute break and then the final session. There are still 9 papers to be presented, one of which is Oliver Herner's best paper that is a case study on integrating a system of systems. Also note that the INCOSE Cafe is still open and waiting for participants. Have a good break.